Hello and welcome to this SPSS one-on-one series with Worry Analytics. Today we look at multivariate analysis of variance, simply abbreviated as MANOVA. Look at MANOVA as an extension of ANOVA, but as opposed to having only one dependent numerical variable in ANOVA, here we have more than one, at least two and above, dependent numerical outcomes that we are comparing against groups of an independent categorical variable. So in this episode, we are using a hypothetical data set that has been modified to illustrate MANOVA. You can download this data set for your practice. The link is in the description of this video. Here is our data set, and we are going to focus on three variables. We have school setting, which is the independent categorical variable with three levels. We have urban, suburban, and rural as type of school setting. Then we also have the two variables, math and physics, which would represent the performance of these students. Now, performance this time round is not one single variable, but there are two variables. We have scores for math and physics. Then the question we are asking ourselves, does the setting of the school influence performance? So this is where we shall use MANOVA to answer this question. So what MANOVA is actually doing, first of all, it is an extension of ANOVA to allow us to use more than one dependent variable. But these dependent variables that you're putting together, they should be related in some way or the other. Or there should be at least a conceptual reason why you're considering to have them analyzed together. Under MANOVA, we are basically creating a summary dependent variable, which is a linear combination of these original variables. We are having a summary dependent variable, which is a combination of mathematics scores and then physics scores. So to run the MANOVA, simply go to Analyze, go to General Linear Model and select Multivariate. On the left, you will see all the variables in your data set, and on the right, you can see the first box is dependent variables. This is where we are putting those numerical outcomes that we want to analyze together. In this case, we have mathematics and physics, which I'm putting under dependent variables. Then we have the fixed factors. In this case, that is the independent categorical variable, which is school setting for this illustration. Shall put it there. With this configuration, we would call this a one-way MANOVA. If we had any other second variable here, that would be a two-way MANOVA. And if we had a numerical variable as a covariate, that one is no longer MANOVA, but it is now an ANCOVA. We have previous videos for that. You can check them out to see what we are talking about. Under plots, we are going to get plots for school setting under horizontal axis. Add that, then continue. Under post hoc tests, we are going to get post hoc test for school setting. So we push it there and we select two keys. This one usually used when you have equal groups. But if you do not have equal groups, most times you select the Shefe method. So for this illustration, I'm going to select two key and then continue. Then under options, you can select descriptives, estimate of effect size, observed power, the homogeneity tests, since this is a key assumption for using MANOVA, and then click continue. Once everything is set, you can click OK. Here are our outputs. First of all, we can see the between subject factors. We have school setting, our categorical variable with three levels, that's urban, suburban, and rural, coded in this way. And we are provided with descriptive statistics, where we have mathematics, physics. We have our scores for both mathematics and physics, disaggregated by the school settings. The means are here, standard deviation, and the numbers in each group. Here is the box test for equality of covariances. One important assumption that you have to look at in MANOVA is the assumption of equality of covariances. And this one here in SPSS for MANOVA is run by the box test of equality of covariance matrix, which tests the null hypothesis that observed covariance matrices of the dependent variables are equal across groups. We want variances to be equal across groups. So we are interested in a p-value that is above 0.05. Based on this, the p-value is 0.999, so it is non-significant, meaning the covariances are equal across the groups. Therefore, the assumption has been passed. We can go ahead and now interpret the multivariate results. Under this table, we are interested in for the variable of school settings, and we have several of the tests here, but usually they all come to the same conclusion. However, if one of these tests here, one of them is showing that it is statistically significant, we always settle in for Wilks Lambda. Then, like we've seen in the previous videos, we have the Leibniz test for equality of error variances. Now, for each of the variables, the boxes test we've seen up here is looking at the overall, whereas this one here is looking at individual outcome variables. And we see that for mathematics, the p-value is above 0.05, meaning this assumption, even at the level of dependent variables, has been passed. So then we have test of between subject effects. We can see that if we looked at school setting for each of these variables, school setting versus mathematics, we see that it is non-significant. There are no significant differences in the means of mathematics across the different levels of school setting. Even when we look at for physics, there is no statistically significant difference in the means across the different levels of school settings, which is still communicating the same conclusion which we've seen for the Wilks Lambda here, that there were no statistically significant differences. Even when we go deeper to look at one variable at a time, one of the dependent variables, mathematics and physics, still there are no statistically significant differences. If there was a statistically significant difference in the mean mathematics scores, this line here, for the different school settings, then we would go ahead and interpret the post hoc tests, and we see, like, if we focus on mathematics, which of the levels of school settings would have been differing from each other. We only interpret the multiple comparisons or the post hoc tests if we had significant differences in the tests of between subjects, and if we also had significant differences in the overall multivariate tests, the Wilks Lambda. So we won't interpret the results of multiple comparisons because there are no differences. They are all the same. Significance levels, you can see all of them are above 0.05. But if, say, urban schools were performing better than rural schools for mathematics, then we would expect to see a significant difference here. Yeah, next you can see the Tukey's HSD showing you subsets. We are seeing that we only have one subset having similar means, and all our groups, urban, rural and suburban, are having similar means. If we had a group that was significantly different from the other, it would be in its own subset, like we saw in I think one way another video. The link is on your screen, you can check it out. We are given the same analysis for physics, and here you have the profile plots. These ones are basically helping you to visualize how the means are moving across the different groups. That one for mathematics and this one for physics. Yeah, so basically that is how you run a MANOVA, a one-way MANOVA. If you wanted to run a two-way MANOVA, I've shown you So next, let me show you how you would present the results of this analysis. So once you've run everything, this is how you can summarize. Here you can provide some descriptives table showing for each of the outcomes, how they are disaggregated by the different groups of school setting. Then we can have a narrative showing the results of the MANOVA. Results of the MANOVA showed that there was no statistically significant difference between the three studied settings, that is urban, suburban, and rural, on the combined subject scores. That is our dependent variables. The Wilks Lambda, we saw it here, 0.98, we put it there, at degrees of freedom 4 and 294 for the error. 292. Yeah, the F statistic at degrees of freedom 4 and 292 for error. That is, the value is 0.733. It is here, you can see. Then our overall p-value is 0.57, non-significant. So based on these results, there was no sufficient evidence to reject the null that students' combined math and physics scores do not significantly differ based on school settings. And the effect size is small, partial eta squared for that Wilks Lambda. Here it is 0.01 here, the partial eta, and the power was 0.236. So the observed power is 0.236, indicating there was a 23.6% chance that the results could have come out significant. So that's how you run a MANOVA test in SPSS. The assumptions to look at, how to interpret the findings, and how to present results for your analysis. So next we look at repeated measures ANOVA, where you have same participants observed at different time points and measurements taken. Don't forget to like, subscribe to our channel so that you do not miss out any of our episodes. See you in the next video.